Good morning, everyone, and welcome to today's webinar, Advancing Methane Slip Measurement Insights from Green Ray and Beyond. We're delighted to have you with us today for this 1-hour session where we'll explore the latest developments in methane slip measurement, a key challenge for reducing emissions from maritime engines. This webinar brings together leading voices from research and industry to share practical approaches, project insights, and emerging perspectives on technologies and regulations shaping the way forward. We're very pleased to be joined by three distinguished speakers today. Kati Lehtoranta, Principal Scientist at VTT and Coordinator of the Green Ray Project. Badr Moutik, Technical Advisor for Marine Decarbonization at GMF, and Dr. Fabian Koch, Head of Section at Environmental Technologies, Air at DNV. We encourage you to share your questions throughout the session in the chat or preferably in the Q&A section, and we'll address them in the specific time slot after the presentations. So without further ado, let's get started. It's my pleasure to hand over the floor to our first speaker, Kati Lehtoranta.
Thank you, Michaela. So, to start with, I will be discussing for the next 10 or 12 minutes about our studies regarding measuring methane with different devices. And this is obviously part of our ongoing Green Ray project. Yes, as we know and we'll hear more today, methane emissions from LNG vessels are coming regulated. And this is one major reason why we also need reliable emission detection and quantification. As there is no universally regulated method for measuring methane emissions, we have done this study and compared 4 different methane measurement methods. So what we have used to measure total hydrocarbons, the flame ionization detector, FID, has generally been the accepted method, like for example in the ISO 8178 standard. Methane can be measured with this equipment as well if it is with a non-methane cutter catalyst that burns all non-methane hydrocarbons. In our studies, we had 2 different FID instruments. The one from Horipa was equipped with this non-methane cutter. Other methods we have used involved gas chromatograph, namely micro-GC from Agilent. Then we also used NDIR. We had 2 different devices, one analyzer from Horipa and then one device from SIG. And then also FTIR was used to measure methane, and we actually had 2 similar units from GasMet. We did studies in engine laboratory and on board. In engine laboratory, we measured the exhaust from a new state-of-art medium-speed 4-stroke dual-fuel engine, namely Wärtsilä 25DF. And then we also had a possibility to do measurements downstream of a methane abatement catalyst. I will not go into details of these technologies today, but just would like to point out that while in this Green Ray project we are focusing on studying what is the methane, what are the methane emissions from the LNG fleet, major focus is put on developing these technologies to reduce methane slip, and that involves both engine technology and this methane abatement catalyst. We also conducted these methane emission studies on board state-of-art cruise ship, MSC's Euripia. There we did measurements on board for 2 engines, both were Wärtsilä 46DF dual-fuel engines. And on board we had FTIR, NDIR, and gas chromatograph to measure methane. And then to the interesting part, so to the results. So in this figure, I have presented the methanes as ppm, so the concentration what we measure from the exhaust. These are now from the exhaust from the engine 25DF. And we have done studies at 5 different engine loadings, and those are presented here. The different colors here present the different devices. So altogether 5 different devices were involved. And when we look at this, we see that both devices, one from SIG and one from HORIPA, that utilized NDIR method, the micro GC and FDIR, show all very similar results with good repeatability. The gray bar representing this HORIPA Mexafeed shows some 10% higher values compared to other devices. If we then take a closer look at this feed instrument, since we had 2 different feed instruments involved, and here we have the total hydrocarbon emissions as ppm from the same situation as on the previous slide. And here we again see a similar difference that this HORIPA feed device was giving higher values than the other feed we had in use. It is possible that this HORIPA Mexafeed was not yet stabilized during the 5-minute measurement period, so the measurement was automized and it was only ongoing for 5 minutes with this device. Then if we look at what we have downstream of the methane abatement catalyst, so in the previous slide we saw ppm levels between 600 and 800 as measuring the engine exhaust. When we have the temperature at the catalyst around 320 degrees, we still measure around 600 ppm level downstream of the catalyst, so only minor methane reduction. But then when we have higher temperatures, we see significant reduction on methane levels. And we have measured levels like 25 ppm or even as low as 10 ppm. And with all devices that were involved here, so we had the feed, we had the NDIR, and we had the FDIR, we have very similar results. The level near 25 ppm is still very well measurable, but then we start to see some higher variance when we go lower, closer to the 10 ppm level. Then similarly, what we have seen on board Euripia from this engine 46DF. So we have here two figures representing two engines. And first of all, we see a higher variance in the methane levels here, how it is changing when engine loading is changing. So we have levels from 600 to 1600 ppms. When looking at the different colored bars here presenting those different devices, we see that all these methods, NDIR, micro GC, FDIR, they show very similar results. There is a few exceptions, what we saw, where the red bar representing the micro GC is giving a bit higher values. But after analyzing these further, we noticed that these were all measurements from our very first measurement day, and unfortunately, the device preconditioning was not enough for the first day. Then for the following day, everything was okay. Then just that you have an idea what emission levels we are talking about. So on the previous slide, I only show you the ppm levels, but now if we calculate these as grams per kilowatt hour, we we can also make some comparison to other studies. And in this figure, I'm representing the results from the 25DF engine and comparing it to other recent studies now with roughly similar size of engine. And what we see here is that this new or state-of-art engine shows low methane slip compared to other recent studies. Low values are already achieved at 25% engine load. Then there is still some higher at this 10% load. That was the lowest mode studied. Similarly, for onboard results calculated as grams per kilowatt hour, and interestingly, there are two other recent studies that have also involved this similar engine. So here the comparison is made to these two other studies. And well, you can see it in the figure as well. So we have very similar results between the different studies. We see low values when we go higher than 40% in engine load, then some lower values when we go below 40% load. Coming to the end, I will make one conclusion related to these different methods to measure methane. So based on this, we have other methods as reliable as FID for methane measurement. And these methods can also be utilized on board. And this is especially important since the FID instrument needs a fuel gas, which is containing hydrogen for operation. And this fuel gas might actually prevent the FID usage on board some vessels. More conclusions you can find in our other recent publication. It's with open access, so everyone can have a look at that. And then I will just end with thanking our Greenray partners who have worked with the project, and thank you for attention.
Thank you so much, Kati. And now we'll move to our next speaker, Badr.
Yes. Right. Okay. Can you see my presentation? So.
Yeah.
Yep. Okay.
Oh, not anymore. I think we lost it.
I think you can see it now. Can you see my screen presentation?
Yeah, now we can.
Right. Thank you. Right. So thank you, Michaela. Good morning, everyone, and thank you for joining us today in this webinar. As been introduced earlier in this presentation, I will walk you through the key findings of the onboard methane slip emissions measurement, practical insights, and industry lessons learned report, highlighting some of the practical insights and sharing the industry lessons learned we've gathered through this research. Right, so just to start with, for the audience who may not be familiar with SGMF are a membership-based NGO. Our mission is to facilitate the maritime sector transition to decarbonization by providing and promoting safe and industry best practice in the safe use of alternative marine fuels, including methane, LNG, ammonia, methanol, and hydrogen. One of our recent publications, part of a series covering different aspects of ships emissions and GHG emissions factors, is the onboard methane slip measurement report, which is the focus of my presentation today. Right, so about the context and objectives of this study and report. I would say this study fits into the broader context of the growing strategic and regulatory framework for reducing GHG emissions from ships, notably the 2023 IMO GHG strategy. In this context, LNG has emerged as one of the main alternative fuels. However, methane slip remains a particular concern. Non-CO2 gases, including also NGO, are considered in the LCA guidelines for the proposed emission factors, and I would say consequently in the JFI regulations as well, in other regional regulations like the Fuel EU Maritime regulations, where shipping companies are expected to demonstrate compliance by reporting representative and robust emissions data of their ships. In recent years, onboard measurement have increased with more in pipeline, as we just seen in the first presentation. This have expanded knowledge, the industry knowledge about generating real-world methane slip data, but they have also highlighted some practical challenges in terms of the implementations on board. As a result, questions have been raised about the practicality, about the feasibility of onboard emissions measurement. The objective of this study is to consolidate industry experience, technical knowledge, and current good practices to provide a first balanced, neutral, comprehensive overview of the current methodology used, challenges, and lessons learned. The study draws on the expertise of stakeholders across the value chain, including service providers, engine manufacturers, and ship operators, as well as key elements from emissions measurement standards like the NTC code and the ISO 8178. It covered 4 main areas: practical implications, looking at different types of measurement instruments, their related installations and monitoring challenges, resource requirements, including technical support needed, the personnel, data collection and processing, covering different types of data required, quality insurance, and finally the onboard operational considerations such as calibration, maintenance considerations, and even the potential impact of measurement activities on the vessel operations. The challenges and lessons learned could be best discussed across 3 identified phases. First of all, from the outset, identified challenges start with the pre-onboard planification phase, where teams should consider technical, regulatory, operational, and logistical considerations. These challenges persist through the onboard execution phase with measurement equipment installations, data collection and monitoring, to the post-measurement phase where data should be analyzed, calculated, and interpreted. So right to start with is the pre-onboard planning phase. Most of the reported challenges can be traced back to insufficient consideration of key elements during the planification phase. Onboard methane measurement should be considered as a multi-phase project, requiring careful preparation across 3 main areas, including technical feasibility, logistics, and operational considerations. On the technical side, the key questions are which measurement methodology to use and which process and equipment are suitable. For example, one of the reported challenges is the adoption of technologies not included in the reference standards. Well, these new technologies, as we have just seen in the first presentation, have shown results consistent with the generally accepted method like the FID. However, concerns remains about their wider acceptability. A critical factor in considering what challenges is correctly identifying and agreeing on the purpose and the scope of the measurement. In other words, what exactly are we trying to answer? This links to the availability of approved service providers and the future scale-up of onboard measurement. Cost-benefit questions also arise, particularly whether the operator or a third party is responsible for the investment, deploying and operating the technology, as well as other indirect costs linked to the operational disruptions. From a logistical perspective, transporting and deploying instruments could also prove challenging. Some technologies require hazardous fuel gases such as hydrogen for feed, which raise additional safety concerns with the ports, authorities, customs, and even onboard ships. Deployment may also interfere with the ship's operations, requiring close crew coordinations and even sometimes creating accommodations needs if extra staff are involved. The single most effective strategy is clear and proactive communication between all interested parties and involving parties with both on shore and on board the ship as well. The second phase is the onboard execution, where most of the practical challenges became visible. First, installation and commissioning. Depending on the technology, installation can range from moderate portable analyzers, as we can see in the picture here, to fixed complex systems requiring more links to the ship's system and the engine control system. Correct placement of the sampling probes, sensors are critical. Notable differences were noted across the case studies. Consequently, preparations with drawings, photos, or even pre-visits to the ship proved beneficial. Deployment of measurement equipment also requires careful attention to the power supply, space, the resource, and sometimes even remote connectivity needed on board. Safety is also a key concern. Specific vessels like cruise ships, operations risk assessment would be needed in the measurement area as well. Calibration methods also show differences across studies, which depends on the measurement period, the technology, which will require valid procedures. Data collection also showed its own challenges, with deviations in operating conditions, notably the incompleteness of data gaps for required loads for the required time, which also been reported differently across different studies. Extended measurement times raises concern for the correct maintenance needed and calibration to ensure continuous performance of the measurement system. Factor to address these challenges is the setting of a correct data quality plan and approve that with the ship's responsible person, since the data collection accuracy depends on the correct alignment with the engine parameters like the power, the load, the fuel consumption, the exhaust flows, and other parameters. Whether data is collected manually or automatically, continuous checks are essential to ensure accuracy and reliability of the results. The final phase is post-measurement analysis, where collected data is converted into tangible emission results. Well, the ISO 8178 and the NTC code method remain the main references for the calculation processes. Other aggregation methods specific to the measurement process and to the technologies have been identified as well. Notable challenges arises particularly when measurements are taken under dynamic load conditions. Data validity presents another challenge. Data gaps, missing data, inconsistent measurement windows, or even estimated input. For instance, LNG and pilot fuel consumptions, or even other engine parameters needed for the calculations of the results can all affect the reliability of results. This highlights again the importance of a clear, well-defined collection and measurement plan. Uncertainty. Uncertainty quantifications also was not consistently addressed across all studies, with varying approaches being applied to represent uncertainty in methane emissions measurement process. The last step is measurement report. Depending on the scope of the measurement, reporting practices may differ in detail and structure. A good best practice is to provide sufficient details so that the results could be audited, compared, reproduced, or even validated by others, including anomalies, assumptions, and lessons learned further enhances the value of the report. Right, so this report findings demonstrate that onboard measurement for methane is absolutely feasible, but it remains a challenging task, influenced by both technical and operational factors, as well as other inconsistencies in the methodologies. As this practice continue to expand alongside technological advancement, there is a clear need for unified technical measurement protocols across the industry and a robust quality assurance framework to ensure reliability and accuracy of the data and results. This is particularly critical for continuous dynamic measurement where standardized protocols are still lacking. Establishing industry-wide best practice will not only enable more reliable and onboard measurement, but also will provide a stronger foundation to inform future policy frameworks. So that's conclude my presentation. The report is available on the SGMF platform and can be accessed free of charge via the provided QR code. A separate report focusing also on the operational and fugitive emissions as a complementary work for the GHG emissions of the ships will also be published soon, providing further insights in this area. And with that, thank you for listening.
Thank you so much, Badr. And now we'll move to Fabian.
Yeah, thank you, Michaela, and good morning to all. I hope you can see my presentation.
Yeah, we can see it.
In my presentation, I will focus on emerging technologies and mainly on the regulatory developments with regard to methane slip. So the greenhouse gas intensity now becomes more and more into the focus, also for the yet to be adopted IMO net zero framework and already in the agreed FuelEU Maritime. And here the greenhouse gas intensity is actually measured in CO2 equivalent, in grams of CO2 equivalent per megajoule of energy the ship is using on an annual basis. And now it comes that the CO2 equivalent also includes methane slip. So all ships under these regulatory frameworks of the IMO net zero framework and also the FuelEU Maritime, they need to report also the methane slip in order to fulfill the requirements of these upcoming regulations. Both of these regulations now contain standard factors as addressed in grams of methane per grams of fuel, depending on the type of energy converter, which is illustrated here on this slide. As you can see, there's slight differences when it comes to the figures itself. These figures are standard factors, as I said, and have to be taken into account when reporting to these regulations. MEPC 83 it was in April this year actually. They adopted a guideline for testbed and onboard measurement of methane and nitrous oxide, which then can be used to apply for an alternative slip factors, alternatively to those standard factors which I've just shown. So the purpose of these guidelines is now defined a testbed and onboard measurement protocol. The measurements itself have to be carried out according to these protocols in combination with the NOx Technical Code 2008 of IMO. It is important to note also that onboard measurements can also be accepted for a fleet of vessels containing similar engine groups. However, it has to be noted here, and here the measurement protocol of IMO makes reference also to NOx Technical Code and the parent engine concept of NOx Technical Code. However, it has to be noted, of course, that the highest methane slip engine is not necessarily the same engine as having the highest NOx emissions. So there still need to individual investigations if the methane slip parent engine is also equal to the NOx parent engine. But anyway, It is possible now, based on these measurement protocols here and these guidelines, to conduct onboard measurements once, not as a SEMS, in a SEMS concept, but once on board of a vessel, and then apply those results also to the similar engines on board of other ships. And then apply alternative slip factors as such for these regulations. To go more into details here, these guidelines also provide some relaxations when it comes to load points for onboard measurements. It also refers, of course, to the standard reference equipment when it comes to methane emissions. And here the guideline actually requires the FID plus a non-methane cutter. However, also other systems may be accepted if proven equivalent results. So that also makes a link to Kati's presentation, which she has shown a couple of minutes ago. Under the IMO net zero framework and these guidelines here, the methane slip will be cycle averaged, applying this similar approach like is done for the NOx emissions. So there will only be one value for single engine cycle averaged slip values available. In addition to these, to the cycle measurements, the methane slip also has to be measured at the 10% mood point. And that also applies to the E2 and the E3 cycle, which normally under the NOx regulation do not require these load points to be measured. So these alternative slip factors also under the E2 and E3 cycle can only be applied under the IMO regulation and also under the FuelEU if measurements have also been conducted at the 10% mode point. In addition to the measurement protocol, these guidelines also require mandatorily a CH4 technical file, which is basically a survey instruction and also contains the measurement protocols and everything related to survey when it comes to the methane slip emissions here. That can be seen as a kind of like equivalent to the NOx technical file. So that is also required to be reviewed and approved by the recognized organization or the class society in that case, in order to apply alternative slip factors under these regulations here. Now digging maybe deeper into the FuelEU Maritime. As already mentioned, alternative slip factors can also now be applied under the FuelEU Maritime. And there already has been circulated a second round of a correspondence group. And the draft has been circulated it was only 2 months ago now in July this year. It is expected to be completed within this year, this guideline for alternative measurement protocols for the methane slip emissions. The draft itself is also based, luckily, making reference in most instances to the IMO guideline here. However, the FuelEU Maritime, in addition to the one-off measurements and the protocols as mentioned in the IMO guideline, also requires so-called engine load monitoring. I will illustrate that in a minute. This is also maybe important to note here, the FuelEU Maritime methane guideline actually also allows for applying alternative factors for this reporting year already, for the whole period of year, for the whole year of 2025, sorry, in case it has been conducted according to the yet to be agreed guideline. For the upcoming years, the alternative factors can only be applied from the date of the measurements only. Okay, this may be important to note that in case you want to apply alternative factors, you have to have conducted, and you already conducted the measurements and fulfill all these requirements of the FuelEU Maritime, then you can also apply the alternative factors for the whole reporting period 2025 already. Engine load monitoring. So go to a bit illustrate the concept behind this. On top of this slide, actually, you see the results of the methane slip measurements. I call it static from the IMO guideline. So here you see the 10% methane slip, 25, 50, 75, and 100% point. And then in order to apply these alternative slip factors also for the FuelEU Maritime, what is mandatorily required is continuous load monitoring for all engines installed on board, which will want to apply these alternative slip factors at on an average of a 30 minutes interval. And then what needs to be done is these 30-minute average load goes into the static, so to say, results from the one-off measurements. The one-off measurements are then interpolated at this load point, and this exercise then has to be conducted for the whole reporting year. So it's all summed up then in terms of fuel consumption over these 30 minutes also. And then the slip factor based on the interpolation over the 30 minutes, and then the whole exercise again is conducted over the whole reporting year. And based on that, then the average slip factor for the reporting year is calculated, and then put into the formula of the calculation of the greenhouse gas intensity. I don't show that formula here because the slides is not big enough, I would like to say. Okay, to further illustrate the FuelEU maritime requirements, so measurements of the emissions according to the IMO guideline. The FuelEU apparently also allows for, in the latest draft, also for total hydrocarbons measurements in case they have been conducted at the 10% load point also. Then combination with this just illustrated engine load monitoring, and then calculating of the actual emission factors. FuelEU Maritime now allows for these measurements. However, they have to be conducted again every 3 years on board of the vessel, or if in case there's a parent engine, so to say, on a test bed, the measurements also have to be conducted every 3 years. So it has to be checked basically every 3 years that the methane slip is still within the prognosticated limits as before. In case, and that was also part of this Green Ray project, of course, in case you have an oxidization catalyst installed on board, then actually you need to conduct also yearly spot checks with simplified measurements that this catalytic reactor is still working as designed. Yeah. So this illustrates the FuelEU Maritime requirements for alternative slip factors, and that already sums up my presentation, and all of us are now happy to receive and answer your question. Thank you.
Perfect. Thank you so much, Fabian. And I think we'll wrap up here. Thank you to everyone for joining. Thank you very much to our speakers for sharing their valuable insights with us today. To all of the audience for joining. We look forward to continuing the conversation and working together to drive forward innovation and sustainability in the maritime sector. Thank you all once again.